Okay, so today we're talking about the electromagnetic. We'll discuss electromagnetic induction, and so let's go to the Maxwell's equations. So again, here are the four Maxwell's equations. As we've said before, these four equations summarize all of electromagnetic phenomena. And today, what we're going to talk about is this equation. The entire chapter is based on this equation. And what this equation tells you is, it tells you that changing time-varying magnetic fields induce an electric field. And the form of the equation tells you what kind of magnetic fields produce what kind of electric fields. Okay. So again, this entire chapter is about time-varying magnetic fields producing electric fields. Okay, now I'll show you the configuration. I'll use my iPad to show you the configuration. But again, that's what this entire chapter is about. Okay. Again, these are the Maxwell's equations in differential equation form. Here they are in integral equation form. So let's see what this tells you. And then I'll show you some simulations. Okay, so I'm going to switch to my iPad. So all right, so here we go. So here's the deal. So we'll go to the equation in a second, but let's say you have a magnetic field like this, and the magnetic field is increasing. So that would mean the density of lines would increase. Okay. Now, if magnetic field is pointing like that and it is increasing, what you'll find is what that equation, this equation tells you, curl of E is equal to minus del B by del T, which is the equation we're looking at. It tells you that you will induce an electric field in this direction. And so an electric field is tangent to this. You'll induce circular field lines, meaning at this point the electric field is there, and at this point the electric field is there, and so on. And if you place a wire there, so there's an electric field induced in space, and if you place a wire there, you can have a current in the wire. Okay, so that's what we're talking about in this chapter. Now, again, add a page below. Okay. So in this, so this is a little extra. You learn about this in Calc 3, and this is Stokes Theorem. And what Stokes Theorem says is curl of E, this, okay, so here's a surface, and you take a surface integral of curl of E, and the curl of E is equal to the line integral. Oops, I better do dA here. Okay, so the surface integral of curl of E is equal to line integral along the curve. Okay, and if you're taking a surface integral in this sense, it's a line integral in that sense. You'll take the line integral. So that is equal to this, and this is Stokes theorem. Okay, so we'll apply the Stokes theorem to that Maxwell's equation that we talked about, equal to minus del S del B by del T. Okay, and now we'll take the surface integral of this. So we'll do the same thing to surface integral of this. And okay, so curl E surface integral is equal to minus del by del T B dot surface integral, and this is minus del by del T, and this term here is called the magnetic flux. This is the magnetic flux denoted by phi. Okay, and this on the left hand side turns into a line integral, and this is the induced EMF along the curve, and this is along a closed curve, and that's equal to minus del by del T of the magnetic flux. Okay, anyway, those are the equations. Okay, so what we are looking at this chapter is, here's what you want to remember. Okay, so if you have a magnetic field that's increasing in this direction, so you have a time varying magnetic field that is inducing an electric field, and the electric field is, the field lines are circular. The further out you are, the weaker the field lines, and the field lines go all the way to infinity. So that's what we're looking at. Changing magnetic fields, time varying magnetic fields, inducing an electric field. Okay, so that's a chapter, and let me show you some simulations now. So all right, so now let me show you a simulation. So okay, so okay, so in this region, what we'll do is we'll change the magnetic field, and we'll change the magnetic field by moving this magnet. You see, so by moving this magnet, I was able to change this magnetic field. And only when the magnetic field changes, you're inducing an electric field all around in this space. And if you happen to place a wire there, since there was an induced electric field there, a current was induced in this wire. So you see, only while the magnetic field changes, you have a current induced in this wire, and this ammeter senses the current. Okay, when the magnetic field is not changing, no matter how strong it is, how strong the magnetic field is, there's no current induced. Okay, so again, what we're studying is time varying magnetic fields in this region are inducing an electric field around it. Okay, and the equation told you the sense of the magnetic field. All right, so so that's Faraday's law of induction. We'll talk about the Faraday's law of induction, the Lenz's law, and energy transfer. Okay, so again, in this picture, if you drop the magnet, the magnetic field inside the loop will change, and that will induce a field. If you move the magnet back and forth, that'll induce an electric current. That'll induce an electric field in this region, which will induce a current in the wire, and you'll have a current in the wire which can be sensed using this ammeter. What you could do is you could pass a current through this loop of wire, then it behaves just like a magnet. This would be an electromagnet. You move the electromagnet back and forth, just like moving this magnet back and forth, you'll induce a current. Okay. What you could also do is you could change the strength of this magnet by passing a stronger current, or just by switching the current back and forth. It's like you're flipping this magnet back and forth. and that will induce a current as well in this coil. Okay. So again, so this is summarizing what we've been studying and what we're going to look at this chapter. We saw then in some of the last few chapters that stationary charges produce electric fields. Well, stationary charges and moving charges both produce electric fields. Magnetic fields are produced by moving charges. So charges at rest will not produce magnetic fields. To produce magnetic field, you have to have charges that are moving. So currents produce magnetic fields. And in this chapter, we'll look at time varying magnetic fields producing electric fields. So we're looking at del B by del T producing electric fields. Okay, so that's what this chapter is about. Okay, what I'll do is I'll pause now and let you guys ask questions.